Hello. So as mentioned just now, I'll go through examples, and the first example I'll go through is an example that concerns rods cutting across the field. Right? Remember, there are two sort of questions. Delta V equals to BLV, and also delta V equals to minus 5. I'll go through this one first, and then I'll go through this one. Let's take a look at the first one. Yesterday, remember, I went through the case where what happens if you have this scenario over here. This is 60 degrees, this is 40 centimeters, this is 150 millitesla, and this is 2 ohms. If I were to push the rod across horizontally at a speed of 15 meters per second, how do I find the EMF induced? First question. No need to do the question yet, but let's take a look at what's the, how do we handle this kind of question. The one that I gave you yesterday was this. It was all nice, all perpendicular, and everything looks really nice. But this time around, I tilted the rod this way. So what modification, if any, if needed at all, should I need to make to this equation so that it will be correct? Let's see who remembers what I said yesterday.
Here I think the sign. Here is the sign.
Yeah, you must always use, remember, in magnetic field, you always think perpendicular. Perpendicular, yeah? So whenever the rod is slanted, you always use the perpendicular distance, the perpendicular length. Now, perpendicular to what? Yeah, perpendicular only has meaning when we talk about two directions, alright? It is the length that is perpendicular to what? Look at the diagram. Perpendicular to a word that starts with V. Velocity, that's right. You see, the velocity is this way. It is the length that's perpendicular. Which means that, take a look, if I move a rod like this, imagine that this rod is infinitely thin. What is the L in this case?
0.
So no EMF. Can? So it is the length that is perpendicular to the rod. That is to say, if I were to give you a scenario, remember yesterday's scenario? If I were to give you this length, how I get metal rod like this, I don't know. But if I can get a metal rod like this, what's the length I need to use? Yes, it is this length. Okay? Cool. Yeah, this is the twist that I can add to the question, but it goes back to this. Okay? Now, with this in mind, I would like you to find the delta V of this scenario. Give it a shot.
So then what we need that resistance for?
It will follow through to another question.
Ampere?
I need current to flow, and when current flow,
Ampere.
there will be something that will happen. Yeah. There's a reason why I put resistor there. Anyone want to drop a text to our Miss Endo?
I'm doing it.
Maybe our lesson is 40 minutes, so look for after this. Okay, I get 0.78. I might be wrong, I just clean the numbers like this, so I might be wrong. If you get the wrong answer, it might be because you didn't change it to degrees mode. It's a common thing. Now, if you have done this, then what I need you to do is to find the current. I need you to find the magnetic force acting on the rod. I need you to find the electrical power using I squared R. And I need you to find the mechanical power using F times V. Once you've done V, I need you to find the subsequent 4 values.
So you mean the resistive force by the
The magnetic field, as the current flow, it interacts with the field to create a force.
Is the current given? Just a given.
No, current is not given. Current
Given
is
formula.
defined.
Is it
Yeah,
given?
defined.
Oh,
Oh.
meters.
It's actually okay. It work the power is I.
Okay, this one I need you to consider FB in the x direction, that means in this direction.
Oh, yeah.
Yeah.
So
It's an interesting thing, you have to be careful with the angle.
is it just IV divided by V? I mean speed. I guess. Yeah, speed. I think so. It's 0.29 divided by 0.02. Yeah, 0.0203. I mean, considering, I mean, I have to assume there is no loss of whatever. Yeah.
Okay, so
Oh, it's fun.
what does F have?
Okay, good question. Let me guide you through. Now, the current can only flow this way or this way, right? Agree? So if the current say flow this way, say for example flow this way, we'll talk about the direction of current flow later. They're only on the Lenz's law. Yeah. So say the current flows in this way, say for example, then it will be this way, this way. So the force is going to be this way or this way. It's not in the x direction. What I want you to find is the force in the x direction. It's a horizontal direction. Okay? Imagine that there's something holding in the y direction, so it won't move.
So, but when are we talking about current? We are talking about induced EMF.
There's an induced EMF, is it a closed circuit?
Yeah.
Current flows. Okay? In the previous examples, I've given you no current flow because I connected a voltmeter across. Yeah?
Sir, I still don't understand why do you have to constrain to x direction? Because we are only moving in x direction. I don't
Exactly,
think
that's why I need to consider the force in the x direction. Because we're moving in the x direction.
But if
Remember,
we
work done is anything to do with work done is equals to the force times distance moved in the direction of the force.
yeah.
So I'm only interested in force is in the direction of the motion. That is where work has to be done. Okay? So go back to your principles.
But if I don't mention that small x after the f,
Oh, then it will be this force is either this way or this way. Then you find that this answer is not equal, and
Yeah.
I want the answers to be equal, and because it leads on to another understanding.
Oh.
There's a reason why it has to be equal.
But my question is, since your movement is only in this direction, shouldn't the opposing force be only in this direction? So we don't have
the force, the origin of the opposing force comes from the interaction between the induced current and the field. So the induced current is over here. It is not
Oh.
flowing here.
understood.
Yeah. So you have to go back to the origin of the opposing force.
Oh.
You need to kind of flow this way, right?
Yeah,
Force
it
will
will
opposite.
flow this way. So, it will flow either way. We'll talk about
Either way,
the direction
either way.
later. Yeah, it flow either
Either
way.
way.
Okay?
So
So
it's
it
this way
will,
or this way?
using your left hand rule, then it's either here or here. So it's either here or here.
But according to lenses, where we use
Of course. Of course. You remember your lessons now, which is good. Yeah. That's good.
yeah.
So we work out all the numbers. These are not given numbers that you have to work it out.
I mean, it's intuitive. You cannot push it this way, then some mysterious force push it that way. Right?
So you are creating energy, electrical energy in the resistor by conservation of energy. The energy must come from somewhere, right?
Okay.
Not really, because it's constant speed, so there's no conversion of kV. So it comes from somewhere.
The a force.
Yes,
pushing
correct.
force.
Yes, correct. I need to exert a force to pull it along. Yeah, I'll say this again when all of you get answers. Because some of you are still struggling to get answers. It's okay. Give you some time. Once you're ready, we'll move on to the next concept. For those of you who are already done and you can actually preempt what I'm going to go through, I'd like you to think about this. I got a ram over here, I got a rod over here moving in a magnetic field that's uniform, and the rod goes like this. If I were to ask you to plot the EMF induced across the rod against time, how will you look like? Think about this.
So,
Yeah.
the last two answers are equal, right?
Yes, they are equal.
Coincidence or
Sorry?
Is it a coincidence?
No, it is not a coincidence. It is based on the certain fundamental rules that you have to obey.
It's the conservation.
Conservation of energy. Yeah. There's no free energy. Even though certain situations you seem to get free energy, but it is not free. Okay? I'll show you some examples. I'll explain to you some. Seems like free energy, but not free energy. Okay, can I check, just to check, everyone gotten this answer?
So what's
The last one, this one, this one? Yeah. This one mechanical. Mechanical means anything to do with forces and motion. So it's force times speed. I need to exert a force over a certain distance at some speed. I do work. I exert power. I apply power. Now, this is conservation of energy, and you need to be explicit. That means it's not just something they remember, but you need to be able to verbalize that the reason why these two are equal is because of conservation of energy. Energy produced electrically has to come from mechanical, yes, correct. And the reason why I need to do work to actually pull it across is because of the opposing force. Right? If there's no opposing force, why do I need to exert a force? Why do I need to exert a force? Then therefore, why do I need to do work? So let's go back to the origin of this whole thing. Energy conservation actually comes from this portion over here. Just now I didn't mention the direction of current flow, but the current flow has to be either here or here. Now where does the opposing force come from? The opposing force, remember that the current either flows here or here, it has to flow here. So it has to flow here so that it interacts with the field this way to produce a force this way. So that there is an opposing force in the x direction, and that's why to maintain constant speed I need to apply an external force. This way. Otherwise, what happens? If I remove this force, what happens to the speed?
So,
It will decelerate. And can you think from the perspective, the lens of energy conservation? What happens to the KE? It decreases, but where does it go to?
The electric energy.
Exactly. Exactly. So if you lift off your force and you don't apply any force, the energy this is still producing power. So it's to zap energy from somewhere. From where? The KE. Okay? So you need to have that fundamental lens, the force energy lens, to look at this whole thing. So Lenz's law, how we actually derive the direction of the force, we must oppose the motion so the direction of downflow this way, is actually another restatement of energy conservation. If you look at that. Without Lenz's law, if Lenz's law doesn't exist, we can get free energy. Right? Yeah. In fact, we can get more energy than we put in. Imagine if the current flow in this way, then the force this way. You just let go, it will produce energy by itself. How good would it be, right? Think of the implication, if you can get free energy, if cars can move without pumping petrol, if machines can run without electricity, think what's the implication?
If I don't have to eat forever.
If you don't have to eat,
Yeah.
That's not.
if you don't have to eat to actually work,
Yeah, I'll still eat even if it's
For fun.
if you don't
Like
need
the
to
natural-
pay to have electricity, wow, this poverty will be less of an issue. Poverty will be less of an issue.
I think it won't be an issue at all.
Yeah. There won't be poverty, I'm not so sure, but it will be less of an issue. When your fundamental needs are being served, you know, okay, let's come back to what I hope to achieve in this question. Yeah, what I hope to achieve. First, application of this. Second, application of this in a twisted situation. Yeah. Third, you must be able to see that through this, energy must be conserved. And the reason why you have to actually do work to move the rod is because of that opposing force. And then we lead on to okay. I I will park that question there, but I like to make sure that you know how to use Lenz's law properly. You have done that before, but just want to make sure through 3 examples, just to make sure that you know how to use Lenz's law properly. Let's take a look, yeah? I'll give you 1 rod and 2 loop question. Let's give a. The rod is this way, the rod is this way, in case you can't imagine. Probably a false scenario. Determine the direction of current flow, induced current flow in scenario A, B, C, and D. Oh, okay.
So, okay. So A is like a rod going upwards.
Yes, right. That means the rod is moved this way,
Oh, okay.
in the presence of the field this way. There are only 2 answers, basically. There can only be 2 answers. You cannot.
So
You see, in this case, some students can tell me the current is flowing up.
so the ring.
How? You're gonna rod this way, the current can.
So the ring should be like.
It's not. Hang on. This is. You mean this one?
No, the first one. A.
This one is not a ring. A rod.
Oh,
A rod.
oh,
Yes, a rod.
Okay, I understand.
This way.
Okay, that's perfectly okay.
Can? If it is a ring, there will be no induced EMF.
No, I think it's this direction.
Okay, let's check this one. It's either in or out. Do you agree? If you have to guess, it's 50% wrong. Answer, if you have to guess. So is it in or out?
In.
Okay. Let's bring this through verbally. Do you agree that the current will flow to produce a force pointing
to be down.
down to oppose the upward motion? Agree? So the force has to be down, the field has to point there, therefore the current is in. You must be able to articulate. Very important. Yeah, understand, not good enough. Must be able to articulate. So it is in.
Sir, I don't understand B. What's the word?
The I increasing. The current is increasing.
So speed is increasing.
No, it's not increasing. This is a current carrying conductor, and the current in the current carrying conductor is increasing. Do you remember that in a current, or regions around the current, there's magnetic field?
So magnetic field is getting stronger.
Yes, right.
And
The direction of the field is important.
This direction now.
You get to figure out.
No, but what's the wrong? Another rod?
This is a ring. A ring. This is a loop. That means a wire loop, I place it here. This is not a rod.
What are we
It's a
looking for,
ring.
sir?
Huh?
What are we looking for, sir?
Direction of induced current. By the way, do you agree that in this, the current can only go clockwise or anti-clockwise?
That's interesting.
Agree? Yeah. So if you have to make a guess, make a correct guess, don't tell me the current is in or out. It's a ring or out the current.
Anti-clockwise, I think.
How can it
Anti-clockwise.
flow out of the ring?
Anti-clockwise.
Give your friend some chance to.
I think.
Give your friend some chance to think.
Sorry, what does I increasing? What's that?
I increasing. Okay, let me explain the scenario. So we've got the current over here. The current in this conductor is increasing. Do you agree that the magnetic field in the region is changing? And because of that, there's a changing magnetic flux over here, right? Flux again over here. Induced EMF, therefore induced current. Agree or not? Therefore, my question is, what's the direction of the induced current? There are 2 ways of looking at this. I'll show you both ways. Okay? I'll show you both ways. So that whichever resonates with you. But one of the ways is easy to explain in exams. I'm going to write this down. How? Take a guess. If it is increasing
Clockwise. Clockwise.
clockwise, let's bring you through the logic and then you decide whether it's clockwise or clockwise. The field in the loop, is it in or out?
In.
In. Okay. It's in and increasing or decreasing?
Increasing.
Okay, increasing. Yeah? Agree? So you agree that to oppose this change, Lenz's law, the current will flow, the induced current will flow in a way to oppose the change that causes it. Yeah? So therefore, in order to oppose an inward field that is increasing, the field due to the induced current must point in or out? Out, right? So the field due to induced current must point out.
Oh,
Now, using a right-hand grid rule
so it's actually
to produce a field out, clockwise or anti-clockwise?
anti.
Yes, correct. So the induced current
That's a bit confusing.
is anti-clockwise. So let's take a step back. What's the procedure? Always identify the change, and then you oppose the change. Then you find out what's the direction of the induced current.
Oh,
And yeah, right-hand grid rule, this is where it comes in.
So when does it oppose the change?
This Lenz's law. The induced current will always flow in a way to oppose the change. But if you take a step back just now, it's actually ensuring that energy is conserved. Yeah. Ensuring that energy is conserved. Yes.
Arguing the conductor, right? The field is like this.
Yes, correct. So it's into the loop.
Yeah, into the loop. And then
And it's
the loop,
increasing.
if the current is flowing this way, right, it should
If the current is flowing this way and increasing or decreasing, because it makes a difference.
right.
You have to give the scenario.
Increasing.
But hang on, let's not change scenario before you even understand the scenario. Do you understand the scenario?
I don't understand the loop part because the loop is perpendicular to the
Yes, right. So the current is producing a field that goes like this
into the loop.
into the loop.
Yeah.
So the field is into the loop and out and increasing.
Yeah.
So in order to oppose that increasing field that's pointing in, I need to push out lah. You want to push in, I push out lah. So I create a field due to the induced current to oppose that change. So how to produce this field? Using a right-hand grid rule, the current has to flow this way. To produce that opposing field.
In this case, you don't show the force, you show the way.
Yes, correct. But the next perspective I'm going to give you is from the force perspective. Okay? Okay? Can I? Okay. If you cannot, then we put on another lens. You take out the field lens, you put on the force lens. Let's check how much you remember. Light current attract or repel? Repel. Light current attract. That means I got two conductors. Attract or repel? Remember, for current is the reverse. Light current attract, light current repel. Okay? Now, look at this segment over here. Okay, just now we talked about the current being anti-clockwise. So, this segment over here, what do you think is the direction of the current? Down or up? So that, you see, by Lenz's law, it try to flow in a way to oppose that change. So do you think you'll try to get closer to an increasing current or further away from increasing current or increasing field? The field is increasing, right? So you try to move away from the field, increasing field to decrease. So does it want to be repelled or attracted? So how does it get repelled? The current over here must flow down or up?
Down.
So anti-clockwise.
Oh.
So you just look at that segment.
That's very If the current in that straight wire is flowing up, there is a force attracting to the right, right? If I look at the right section.
Yeah.
So it's
Okay, this one, okay, what Ren is saying that if this one, then you attract, alright? But which one is nearer?
yeah, the left one. So it does not move that way, but it also maybe.
Yes, and that's a very good point. That's a very good point. You see, opposite current, it will try to, no, actually it also, yes, right. So it will push here and then this will
But then what about between
now,
this?
can you see it? Hang on. Keep it. Now that's a very good point by Ren over here. Can you see that this one is the same direction, so you try to attract. This one will go inwards in a sense. This part of the current will be attracted because it's like current to this one up. And you see that this one will be repelled.
Yeah, but
hang on, let me finish. So this one will be repelled, which means that it will be pushed away. So this is pushed away, this is pushed inwards. What happened to the area? So can you see that whatever it does, it is trying to reduce the area, to reduce the
flux.
Because flux is dependent on field and area. Right? So whatever happens, right, is whether it tries to get away towards the right by repelling, or it is trying to decrease the area, whatever that happens is to try to oppose that change. It is trying to decrease the flux through whichever means.
Then what about this two current inside that loop?
That one you'll try to expand. That's why I
But which one is?
I'm sure that the reducing flux effect is stronger. Yeah, otherwise you'll be violating Lenz's law already.
I don't know if I missed something. How do you know that the induced current is anti-clockwise?
How do I know that induced current is anti-clockwise? Okay, through which one? The field one, which I mentioned, the first one, or the force perspective?
Because if you want, when you get the force perspective, it looks like you just started doing that.
No. What I look at is this portion over here. I started with clean state, I look at this portion over here. I know that the field, the current is increasing, so the flux is increasing over here.
Yeah.
So this will try to decrease the flux by moving further away. Right? So this part will definitely be repelled away. So using my knowledge that light currents attract and light currents repel, this has to be opposite
So
current.
actually that came first, or
Yes, the increasing flux still comes first.
Okay.
Correct, correct, yeah, correct.
So if the thing switches, then isn't the area just switch? Because it's circle.
The same length in different shapes has different area. Yes, actually it has different area.
Alright,
Circular is actually, I think if I'm not wrong, correct me if I'm wrong, you know geometry, I think it's the biggest area of any given length. Any math genius over here? Given any length of a closed loop, is circle the biggest area?
Should be.
I think so. I think so. Circle is the biggest area. You can prove me wrong, lah. Yeah, I think circle is the biggest area. Can?
Sorry, you can relate the circumference and the area equation in
Yeah, I think it is. I don't have a proof, but I think it is. Now, C. You see a drive. If I got the current that's pointing up and I pull it away, try to go through that same argument. The field is pointing in, still in. Is it increasing or decreasing?
We don't know.
It's being pulled away. It's decreasing, correct?
Oh.
So the induced current will try to flow in a way to produce a field that's pointing in or out.
Huh? Still out what?
It is
If it is pointing in and really getting weaker, you point out, wouldn't it get even weaker?
Even weaker is if it's pointing out.
If you're getting weaker, you try, in order to oppose it, you should try to make it stronger. Right? I'm trying to oppose that weakening. How do I oppose that weakening? You make it weaker? Or do you make it stronger? Oppose. The keyword is oppose.
I'm confused. What is weakening? As it moves out.
Lower. Lower. That means the flux is getting lower.
Oh.
It's pointing in and getting lower.
Oh.
So how do I oppose that lowering of flux? I try to increase it, right? So therefore, the field due to the induced current must one in. That's why it goes clockwise. Now let's test our hypothesis. If this goes clockwise, does it attract or repel?
Attract.
Opposite. You pull it towards the right, the force is towards the left. So this is one way to test your answer, see whether it's correct by another approach. Let's test on the other approach. This one attracts and this one will repel, right? I mean by the same logic. Therefore it's trying to try it out, but cannot really. Like tries to make it bigger.
But again, sir, what about this
There you
direction?
come down. This one.
No, I mean
The effect is to try to enlarge it, whereas the other one is try to decrease it. The general effect. Okay?
wait, sir, that force direction is
I'm
spontaneous.
moving it this way.
there's no shift.
Huh?
Yes,
No,
right.
it's
That's
not
the trick.
possible.
There's no induced current.
Yeah, it's not possible.
There's no induced current because the flux remains the same.
Yeah.
Which one?
The
Can see
D,
now?
yeah.
Can see now, the field, because the field only changes with this distance.
Field line is the
Yeah,
same.
it's a trick, huh? There's no induced current. So there's no, there's no need to apply this. Cool. So hopefully, I mean, must go the examples, because if you are not sure, you must look through the examples, then you see the logic, how it applies. Because it's easy to remember Lenz's law, but to apply it, there's a certain thinking process. Yes.
There's no induced current because it's parallel, right?
in the sense that there's no change in flux, because the field at different points over here, it remains the same.
Okay.
Yeah, so there's no change in flux. Cool.
So is it like when there's a change in flux, then there'll be a
Induced EMF. It changes in flux linkage. There'll be induced EMF.
to oppose the change in flux?
You're talking about Lenz's law.
Yeah.
If you're talking about Lenz's law, whenever there's an induced EMF and there's induced current, there must be induced current. The induced current will flow to oppose that change and induce it.
Oh, so it's induced current.
Induced current, correct. Yeah. Be very careful. Lenz's law is the induced current, not induced EMF.
Okay.
It's the induced. Can? Cool. Now, we don't have time for the one that I want to do, I'll do it tomorrow. Let's go through this example. It's a very interesting example that combines what you learned last year, projectile motion, and what you learned now. So I got a rod that goes down this way, down a ramp, and then it goes into projectile motion.
So is the ramp frictionless?
Frictionless, yes, correct. The B is uniform throughout, and yeah, no tricks. Just a thing going down a ramp and goes into projectile motion. Using your knowledge of delta V equals to BLV, how does it change?
This. Yeah, this.
It brings up another idea later on. Okay, let's break this down into two parts. Part 1 and part 2, yeah? Before and after the ramp. Before the ramp, is the speed increasing or decreasing?
Increasing.
Increasing,
Yes,
right?
of course, yeah.
Increasing, right? Increasing at a uniform rate or changing rate?
Uniform rate. Actually.
Because the acceleration is g sine theta along the ramp.
But sir, we're not sure because there's an opposing force.
This is just a rod. There's no induced current, so there's no opposing force. In order for you to have opposing force, you need to have BIL.
Isn't this the?
That's the field. There's a B, but where's the I? There's only a rod. If you just hold a battery, is there induced current?
Oh, the rod does not have thickness.
The rod doesn't. It's not connected to external circuit
Oh.
like this. The one that we did just now.
Because the other one's in the Bluetooth thing.
Yes, there's a resistor.
Yeah.
Remember? So this is just a rod. So there's only induced EMF.
Ah.
Okay? So this doesn't change, this doesn't change, this increases at a constant rate. It is equals to AT, U plus AT. Let's assume this is 0. So it is increasing at a uniform rate.
Get
Yeah,
it.
okay? So yeah,
So increase. Linear
part 2 is the interesting part.
decreasing.
Okay, think about this. When I have a rod moving this way, and when I use the equation delta V equals to BLV, do I use this V? Do I use this V? Or do I use this V?
X lah.
X, right? Think perpendicular, right? You're always the perpendicular one that cuts. So it is this way. Now to answer the question of how it looks like over here, how does the horizontal velocity change?
Decreasing to 0.
Projectile motion. Projectile motion.
Oh yeah.
Oh yeah. Yes.
Oh yeah.
It's very tempting for you to think that it increases further because it's faster and faster. No, it is.
So it's constant. Ah.
That's the twist. Yeah. And different motion, different kind of physics. Yeah, so this is it brings out the idea of the horizontal velocity. Not just horizontal, it is a velocity that cuts the field. Okay? So I think it's a nice closure for the lesson. I think we close this part nicely. The next time I see you tomorrow, I'll go to loop and then rotating loop. Cool. Okay. And why it leads on to understanding why do we use AC for transmission and not DC. One is advocated by Tesla, one is advocated by Edison. Yeah. And if you ever have the chance to watch, there's a movie on the two of them, the rivalry between the two is really interesting. Must go and watch it.